Just waiting for the display to show up. Okay, it's the last day. I know it's a lot, and it's a morning as well. But I'm going to keep my presentation. I'm going to leave a lot of cryptographic details out of my presentation. I'm going to give an intuitive introduction to what the encrypted computer is. And I'm also going to tie it back to my previous presentation back in 2025. But before that, hi, I'm Janmajaya. I work at Phantom Zone, and I also run a company called Doxa Labs. And I'm going to be talking about the encrypted computer. First, what is encrypted computer? You can think of the encrypted computer as a machine that executes encrypted inputs on encrypted programs, and it produces selectively either public or encrypted outputs. So you can think of this as a black box machine, in which it just takes the inputs, produces the output. You cannot look inside it, and it cryptographically guarantees that no one can look inside the machine. Now, this might look like a black magic, but today, I'm going to describe you a couple of methods on how to achieve that and sort of make it clear that it's not black magic. OK. So the first path that we started to explore to build this encrypted computer was Phantom. You can think of Phantom as a RISC-V virtual machine that is built using FHE circuits. And in EthPrague 2025, I introduced Phantom as a prototype. Back then, we estimated that Phantom as a RISC-V machine, which can execute arbitrary code, would take roughly 2 cycles per second, which is immensely slow than ZKVM that Jody presented previously. But we finalized the implementation last November, and it takes approximately 600 milliseconds on 32-core CPU. And we expect roughly 100 to 150x improvements using GPU, but with the caveat that we do not have a GPU implementation yet. But there's a problem that Phantom faces. The problem is not just particular to Phantom, is because we're using FHE. In FHE, someone needs to hold the secret key. Who holds the secret key in this case? Well, the best practical answer today is something called threshold FHE committee. And in my opinion, this is not ideal for 2 reasons. First, secure threshold systems are really hard to bootstrap in blockchain systems. People have been trying this for, I don't know, half a decade now. It is, in my opinion, it's not doable. Third, collusion, particularly for threshold FHE systems, is not possible. It's not possible to detect. You cannot detect whether someone has colluded and leaked the secret and hence leaked privacy. And of course, threshold committees, they may work for closed and gated systems, but when we speak of closed and gated systems, those are not decentralized systems. OK. Which started, which roughly 2 years back, started us to question whether there's any other path apart from this, and that did a transition from FHE to something called obfuscation. And back then, obfuscation was this fancy thing for which there existed this impractical construction that would take, I don't know, a gazillion years to execute, et cetera, et cetera. OK, so the roadmap for today is that first I'll tell you what is obfuscation. And then I'll tell you about our evolution and thought about around FHE plus obfuscation. And then I'll give you an update on the local mixing approach to obfuscation and an update on other approaches to obfuscation. OK, what is obfuscation? Obfuscation simply says that you need a method which takes a program, does something to the program, and produces an obfuscated circuit, with the guarantee that if you give the obfuscated circuit to someone else, the other person should not be able to recover anything about the program other than the input and the output. So for example, you take a program, you put your secret key inside it, and this program signs on your behalf. Let's just say Ethereum transactions. You can now obfuscate this program using the obfuscation procedure and produce an obfuscated circuit and give it to someone else so that someone else can sign the Ethereum transaction on your behalf without learning your own secret key. Now, if you are in Ethereum space for a while, you would understand why this is useful. One instance why this is useful is because now you can have smart contracts signing stuff for you based on some condition and have the secret key. OK. So back in EthPrague 2025, I presented this one method of obfuscation, which was you have FHE. In particular, you have publicly verifiable FHE. And you have Phantom that takes in encrypted inputs. It takes in, OK, for some reason, it's not that visible. OK, sorry. It takes an encrypted program, and it takes in encrypted inputs, and it executes the encrypted inputs and outputs two things. It outputs the encrypted output and a proof. OK? We're using publicly verifiable FHE in the sense that it's like ZK plus FHE, if you want to look at it that way. It's not ZK in the sense because ZK is zero knowledge. Publicly verifiable means like it's just succinct proofs. It produces the output and proof of execution. And then we obfuscate a very small functionality that I refer to as the conditional decryptor. And this conditional decryptor takes in the proof. If the proof is valid, and then it will decrypt the output ciphertext. Otherwise, it returns null. And the reason we do this, and the reason we need a proof, is because the conditional decryptor would decrypt anything. The proof sort of like makes sure that it only decrypts the output of the Phantom VM. Now, the logic back then, and I think that still today, if I look back, seemed sound, in my opinion, but because obfuscation as a cryptographic primitive is harder than FHE. Intuitively, logically, it should be more expensive. So you should try to lift up as much of compute as possible into something that is more practical today, which is FHE, and only limit obfuscation to a very small surface area, which is this conditional decryptor. But however, looking at the progress that we've made in the past year, it feels like it's just an intuition today, but it feels like it would be practical, perhaps more practical, to obfuscate programs directly. Hence, in my opinion, or at least moving forward, we as a research group, I'm working with other people on this, are going to discount this method out of FHE plus conditional decryptor. Which brings us to the next topic, which is the local mixing approach. This is one of the methods of achieving obfuscation, and this is one of the methods in which we have progressed quite a bit in the past year. So what is local mixing approach? You can think of local mixing approach as a new approach to obfuscation that is efficient, but it is not yet provably secure. In local mixing approach, you first shift your computational model. You go from circuit land to reversible circuit land. What is a reversible circuit? Intuitively, you go from this Boolean circuit model to this reversible circuit model. And in a reversible circuit model, the logic is pretty simple. You never lose information. From input, you get the output. And from the output, you can always get to the input. That is not true for Boolean circuits. For example, an AND gate, you lose information. You lose the inputs. But in a reversible circuit, an AND gate would look something like this, where you, in addition to getting the output, you also get to the input as the output. So you never lose information. In reversible circuit, the goal is pretty simple. You need to find an obfuscator method which, when applied to circuit P for program P, outputs an obfuscated circuit that satisfies this definition of obfuscation. Like, you should not be able to learn anything about the obfuscated program. Sorry, you should not be able to learn anything about the original program P from the obfuscated program. So in EthPrague 2085, roughly a year back, I presented local mixing as a two-step procedure called inflation and kneading. In simple words, what is inflation? Inflation adds a lot of redundancy to the circuit. It takes small paths, small gates, small pairs, I suppose, in the original circuit and inflate it, add a lot of fat to it so that the circuit becomes large. And intuitively, you can think of it as like adding a lot of rubbish data to the circuit so that you cannot figure out what it does. And then we do something called kneading, which is the third slide here. In kneading, you're just jumbling everything together. You're just mixing it well so that no one can unroll the obfuscated circuit. And of course, the exact procedure is way more complicated than what I'm describing, but intuitively, that's how it feels like. And a way to test, I presented something called heat map. You can think of heat map as trying to find correlation between computation across the obfuscated circuit and the original circuit. Intuitively, you can think of this is what I refer to as heat map. On the y-axis, you have the original circuit. Sorry, on the x-axis, you have the original circuit. On the y-axis, you have the obfuscated circuit. And each axis, the graph represents the computation flow. And if the computation is correlated, you would see a straight line. If the computation is not correlated, you would see something jumbling here. By the way, this is not obfuscation. This is just two random circuits that I just sampled. Okay? So we do not have, we have a heat map that looks like this, but, this one is fake. Okay, and then I ended with an experiment that sort of showed a hazy line, like something that is ideal, but with a hazy line. And I made a claim that if you do more kneading, you'd be able to erase the line. But then we went back to whiteboard. Turns out, doing more kneading steps would erase the line, but it would make it much more harder to look at. But there were few critical questions that we were not able to answer. First is when to stop kneading. You just keep doing for years and years and years. Second question was whether the adversary, assuming the adversary know which was the last kneading step, wouldn't the adversary be able to start unrolling the thread from the last kneading step? And what about second-order attacks? For example, heat map is this first-order attack. Second-order attacks are something like differential analysis, where you try to figure out something from the degree of the computation. And the differential analysis is pretty common in symmetric crypto. And why can't anyone apply that to our methods? So this led us to sort of quickly enhance our methodology and segment a procedure into a pre-processing step, which introduces high algebraic degree to the circuit, and a 4-step repetitive process. And I'm quickly going to go through them. So the first step is high algebraic degree. What we want is, first you can think of each wire in the reversible circuit as a polynomial. If you take a random reversible circuit, the degree of the polynomial would be very low, not that high. We want to make sure that the degree of polynomial of each wire is high. So what we do is that we XOR the wires together. So we take one wire in one computation, XOR with the other one, and we do it randomly. This increases the degree, but this changes the functionality. Then we introduce something called gadgets. I'm not going to go into detail of what is the exact structure of the gadget. But think of this gadget as this magic thing which reverses the computation so that you get to the original functionality. By the end of this pre-processing step, you should have a circuit where each polynomial, where each wire polynomial has very high degree. So you get around differential analysis. Okay. Now, we come to shuffles, which is the first step in the loop. I'm going to describe 4 steps, and we do them repeatedly for 3 to 4 times. Shuffles. You can think of intuitively shuffles as shuffling the wires and shuffling the gates. To be more specific, this is the method. I can go through this, but this would take time. But intuitively, you can think of it as shuffling the wires together and shuffling the gates together, making sure that the functionality remains same. Shooting. Shooting literally means what it says, basically. You take each gate and you try to shoot it as far as possible in the circuit to the extent it is allowed without changing the functionality. You just shoot it as far as possible, and that's it. And this is useless until you do the third step, because this doesn't change the structure at all of the circuit. This is useless until we do something called locking. So what is locking? Locking takes the circuit. For example, let's just say you have a 5-gate circuit. It takes the first 2 gates, replace them with a large identity circuit. Identity circuit meaning that it computes nothing, but it just looks like a large chunk. So it takes the first 2 gates, replace with a large identity circuit, and then do this repeatedly for each pair of gates again and again and again and again and again until it reaches the end. You can think of it as we have taken the computation of the circuit and we have introduced redundant blocks within this circuit which you cannot compress, and hence we have locked the circuit. Okay? But this is a randomized procedure, which is why after this we run something called compression. Compression simply means we just have a really good compressor that just try to reduce the size of the circuit. That's it. It's like a brute force procedure. We run it like, for a couple of minutes, and it tries to reduce the size of the circuit. And then we go back to shuffle, do it again, shuffle, do it again. The more time you do it, the better the results are. But we expect that doing 2 to 3 times would suffice. Okay. Now, I'll show you some fancy graphs. Now, this is what a reversible circuit looks like. You can think of the vertical lines at the gates, the horizontal lines at the wires. Each gate, I can describe you what the gate is later. If you only do shuffle, this is what the circuit looks like. You can see big chunks here. And you can see the data lines. What are data lines? Data lines are the original wires, original gates in the original circuit. You can see in this particular subsection, by the way, this is a huge circuit. In this particular subsection, you can see 2 data lines that are visible. This is with shuffle only. And then we move from shuffle to shuffle plus shoot plus lock. And then you would notice that the original data gates have been jumbled up with random gates. And they're no more visible. And we measure the entropy of each wire in this particular circuit. It's nearly 0.5. Ranging, taking a scale from 0 to 1. And the heat map looks fantastic. Look at this. Anyhow, the blow up in this circuit is roughly 100 to 1000x. With 2 to 3 rounds, the more you do, the more the blow up. But again, we are trying to make sure that the blow up remains as minimal as possible. And this is good news, because I work in FHE, and FHE has 1 billion times blow up. This has 100 to 1000x, which is way, way, way better. What's next? So I think we're nearing the end of our first iteration, which was a year-long iteration. We would be releasing a challenge with a collection of obfuscated circuits, putting our method to test and see what happens. And one of the best ways to contribute to this effort is to try breaking this challenge. Reach out to me and try breaking this challenge. If you want to be notified when the challenge is released, which would be roughly in 1.5 to 2 weeks, depending on how efficient the code is, you can scan this QR code, enter your email, and I'll send you an email when the challenge is out. Okay, now other approaches. The other approach is from Machina.io. Machina.io. It's a team from Ethereum Foundation that is working on building obfuscation from secure approaches, so not doing a departure from existing cryptography the way we have done, but instead trying to use existing cryptographic primitives to build obfuscation. They have pulled off something that, in my opinion, I told the person that it's not possible a year back. they've pulled out an exact implementation of Diamond IO, which is an obfuscation scheme based on secure cryptographic primitives. The implementation has practical lattice parameters, but again, astronomical execution parameters, meaning it will take, I don't know, how many years before I die for it to be executed. The key improvement in Diamond IO is something called key homomorphic encoding, and just think of it as like a step towards getting obfuscation using lattices, which is a cryptographic primitive. And the next step for them is to find an efficient technique for homomorphic encoding. You can check out their work at makinaio.com. OK, cool. OK, so by the way, I'm just the person who's speaking here. There's a huge team behind this. For local mixing, I would try to credit Ron Canetti, Claudio, Eduardo, Andre, Nicholas, who has done a lot of code. He's written most of the code. Eli, who's a really good PhD student at BU. And Agiman, again, a PhD student at BU. For Phantom, most of the work was done by John Philippe and Rasul. And for Makina.io, most of the work is done by Sora. And that's it. Thank you.